You know, in data science, we love a good straight line. They're just so simple, right? Predictable, easy to work with. But what happens when your data just refuses to play by those straight line rules? Well, today we're going to unlock the curves. We're diving into a super powerful tool called polynomial regression and figuring out how to model all those complex curved relationships we see out in the real world.
So, our go to tool for spotting trends is almost always linear regression, right? It's simple, it's powerful, but it has this one huge assumption baked right in that the relationship between our variables is, you guessed it, a straight line. So, what happens when reality is, well, a little more curvy?
And that is the core question, isn't it? Because in the real world, things are rarely that simple. I mean, think about it. Population growth, the arc of a ball you toss in the air, or even how a disease spreads. These things curve, they accelerate, they change direction. A straight line just can't keep up. It completely misses the real story. Okay, and right here, the problem becomes crystal clear. Just look at this. The data points are making this really obvious U shape. Now, if we try to force a straight line through that, well, we miss the mark. And not just by a little, but by a lot. We're not capturing the real pattern at all, which means our predictions are going to be way off. This is like the classic textbook example of where linear regression just completely falls short.
So, if straight lines are out, how in the world do we start drawing curves with math? Well, the answer is actually a brilliant extension of the linear regression we already know. It's time to introduce the hero of our story today, polynomial regression.
Okay, so what is it? At its heart, polynomial regression is all about giving us the flexibility to grab onto those nonlinear trends. So instead of a rigid straight line, we're using a polynomial equation. And yeah, I know that might sound intimidating, but just think back to high school algebra, with terms like x squared or x cubed. That's what lets us create a curve that can actually bend and shape itself to fit our data. And here's the key difference when you put them side by side. A simple linear model has just one coefficient, one little knob to turn for our variable x. But a polynomial model, it starts adding new terms, x squared, x cubed, and you can keep going. Every single new term is like giving our line another joint, another place where it can bend and curve. This is what gives it all that flexibility to fit much, much more complex patterns.
So, how does this actually work under the hood? It's a surprisingly clever trick, actually. We start with our plain old input variable, x. Then we create new features just by taking x and raising it to different powers. So we get x squared, x cubed, and so on. And here's the really cool part. We then fit a standard, normal, linear regression model using all those new features as our inputs. So even though the final result is a beautiful curve, we're still using the good old engine of linear regression to get there. It's pretty smart.
Okay, but this newfound power brings a new challenge. It's a classic case of with great power comes great responsibility. Because now that we can create curves of pretty much any complexity we want, we run smack into what I like to call the Goldilocks problem. We have to find a fit that's not too simple, not too complex, but you know the rest, just right. So on one end of the spectrum, you've got underfitting. This is when our model is way too simple. It has what we call high bias. It's kind of like trying to draw that U shape we saw a minute ago, but all you've got is a straight ruler. You're going to completely miss the point of the data. And your predictions? They'll be terrible because the model just hasn't learned the real relationship. Then, on the total opposite extreme, we've got overfitting. This is what happens when our model is way too complex. It has high variance. Imagine a curve that's so flexible and wiggly that it twists and turns to hit every single data point perfectly, including all the random, meaningless noise. Now, it'll look absolutely perfect on the data it was trained on, but the second you show it some new data, it's going to fail, and fail spectacularly, because it didn't learn the trend, it just memorized the noise. So the whole goal here, the entire game, is finding that sweet spot right in the middle. We need a model that's flexible enough to actually capture the true pattern in our data, but not so flexible that it gets distracted by every little random blick.
And this fundamental challenge actually has a name. It's called the bias-variance trade-off. And listen, this isn't just some polynomial regression thing. It's like a universal law in machine learning. As you make your model more complex to lower that bias, you almost always increase its variance. And it works the other way too. The real art and science of building a great model is finding that perfect degree of complexity that minimizes the total error, not just one or the other.
All right, so we get it, it's a balancing act. But
how do we actually find that perfect balance? Let's get practical and look at the strategies data scientists use every day to get it just right.
So how do we choose the right degree for our polynomial? I mean, that really is the million-dollar question, isn't it? Do we need a simple squared curve, or do we need something way more complicated, like to the power of 10? Choosing this degree is what we call setting a hyperparameter. It's basically the main knob we can turn to control how complex our model gets. And yeah, it can be the trickiest part of this whole process, but luckily we've got some systematic ways to figure it out. There are a few common ways to tackle this. One is called forward selection, where you start super simple, like with a straight line, and you keep adding more complexity, 1 degree at a time, checking at each step to see if the model's actually improving. Backward elimination is just the reverse. You start with a super complex model and start chopping pieces off until performance starts to suffer. But really, the gold standard, the one everyone trusts, is cross-validation. This is where you smartly split up your data, training on some parts and testing on others over and over. It gives you a much, much more realistic idea of how your model will do on brand new data it's never seen before. It is absolutely our best defense against that dreaded overfitting. Okay, that's enough theory. Let's connect all this to the real world. Where does polynomial regression actually show up? Well, the answer is pretty much anywhere you can find a curve. Think about biology for modeling the nonlinear growth of cells or tumors, or finance for trying to capture the cyclical ups and downs of the market. Public health officials use it to estimate the spread of a disease. Engineers use it for everything from predicting the trajectory of a rocket to fine-tuning the speed control in a self-driving car. I mean, it is an incredibly versatile tool. And believe it or not, it gets even more powerful. We're not just limited to one variable. I mean, check this out. What you're looking at is called a response surface. It's a polynomial model, but it's using 2 variables, let's say temperature and chemical concentration, to predict an outcome, like the yield of a reaction. It creates this complex 3D surface, and what that does is it lets scientists pinpoint the exact perfect combination of inputs to get the absolute best result. This is a game changer for optimizing all kinds of industrial and manufacturing processes. All right, let's start to wrap this up. I want to go over the most important takeaways and, more importantly, the common pitfalls you really need to avoid when you're using this powerful technique. Okay, first and foremost, and I really can't say this enough, watch out for overfitting. It is without a doubt the single biggest risk. Second, be super careful with what's called extrapolation. That's when you try to make predictions outside the range of your original data. Polynomial curves can go absolutely wild, shooting off to infinity, making any predictions out there completely useless. And finally, just be aware that these models can be sensitive to outliers. Sometimes one single extreme data point can grab your curve and pull the whole thing out of shape. This quote here really captures the core philosophy you should have. Parsimony is just a fancy word for simplicity. It's your best guide. The rule is, don't add complexity unless the data is practically screaming for it. Remember, the goal isn't to build the most complex, wiggly model you can. It's to find the simplest model that still tells the story accurately. And really, that leaves us with the central challenge you'll face in almost all of data science: finding the right balance between a model that's simple enough to be true and one that's complex enough to actually be useful. Polynomial regression is an amazing tool for finding that balance. But just remember, the real skill isn't about building the most complex curve possible. It's about finding the right one. The goal, as always, is to just let the data tell its story, even when that story has a few unexpected twists and turns.